Well, good morning, everyone. Thanks for attending and thank you for having me today here. I'll be going to talk about irrigation. So not much about nitrogen. Since it's a nitrogen conference, there is a component that I'll be talking about nitrogen, but how it integrates with irrigation. So for the first part of this talk, I'll be covering a project that we are doing here in Minnesota at 2 locations, which integrates irrigation and nitrogen. But then in the later slides, I'll be also talking about some new advanced irrigation practices that we are trying to figure out how to do that in Minnesota. So variable rate irrigation, precision irrigation project that we started last year. So some results from that study. So in my first slide, I want to share with you some statistics about irrigation in Minnesota. All right, so this map on the left shows you the available water storage at 0 to 40 inches, and most of the central sands region of the state is having very low water holding capacity or available water storage. And this place coincides with the active agricultural irrigation permit wells where mostly the irrigation is being done. So the right map is the DNR irrigation permits. So these blue dots are the irrigation wells. So most of the irrigation happens in the central region of the state. The reason behind that is the soils. So these soils, they cannot hold much water for a longer period of time. So they need irrigation for crop production. So that's the main reason why we are irrigating these soils. But at the same time, irrigation is important, but there are nitrate leaching concerns that are related to agricultural irrigation in these regions. So mostly because these soils are coarse in texture, sandy soils, and having very low depth of groundwater, so very shallow aquifers below these soils, so they are prone to nitrate leaching. So when we apply more water than required, that water very quickly, along with the agricultural fertilizers, go to the groundwater and contaminate the groundwater resources. So that's one of the major concerns here in Minnesota that we are facing in irrigated agriculture. Not much about quantity. There are some places where quantity is a problem, water quantity, but quality is the one that we are right now dealing with in terms of irrigation. So one question that usually people ask, why nitrate loss occurs. So I'm not going into the nitrogen cycle, how nitrogen is being converted to nitrate, but we all know that when we apply this fertilizer, this is converted eventually to nitrates, and then through the action of soil microbes. And then this nitrate is readily available for loss if we apply more water than required, or then it can be stored by this soil water. All of this is going to be lost in runoff or in the deep percolation. And in sandy soils, we don't have that much of runoff. So all of that water goes below the root zone and eventually to those shallow aquifers. So that's the main problem that we have here. How irrigation is related. So I put this figure here that describes all the inputs and outputs of water to this agricultural system. So we have irrigation and rain, those are the major water inputs, and deep percolation and runoff and evapotranspiration, that is how much your crop is using that water, are the major outputs. Anything that's stored in that root zone is the soil water. So from our research projects, what we are trying to do is manage that soil water, how we can effectively manage that soil water so that we do not lose that water in runoff or deep percolation, and keep all our important nutrients, nitrogen, fertilizer in that soil water. So that's the main role that we are trying to accomplish here. So one strategy that we can use is the deficit or limited irrigation management. So what that means is that in this soil water zone, if we do not fill this soil water completely and use some reduced levels of irrigation, rather than filling it back to field capacity, we fill at certain levels so that we make sure that we are not losing that water to the deep percolation. We use these strategies which are limited, reduced, or deficit, whatever name you want to give it to. You can, it's interchangeable. So all of these means the same meaning, which means that to apply less water or irrigation water than required to meet the crop water demands, but also to target the grain yield, the balance in grain yield. So maintaining the grain yield at the same time, using less water to give to the crop for crop evapotranspiration. So there are basically two ways how we can do it. The first is withholding the irrigation at different growth stages that are less sensitive to water deficit. So for example, in corn, so corn is very less sensitive to water at the early growth stages and at the end of the season. So we can apply less water or no water at those stages and only concentrate our irrigation treatments or irrigation water in the center or the middle of the growing season, close to vegetative tasseling or reproductive, starting of the reproductive growth stage when corn is really sensitive to water stress. So that's the one strategy we can use the deficit irrigation, like no irrigation or very less irrigation in these stages, which are not very water sensitive, whereas putting most of our water in the most sensitive parts. The second strategy is reducing the percentage of the full irrigation requirement. So what does that mean? We keep on irrigating throughout the growing season, no matter what growth stage it is, but we do not put the 100% irrigation requirement. So 100% irrigation requirement is filling the soil profile back to field capacity. However, we don't do that. What we do is we apply irrigation, but in limited amounts, so reduced irrigation throughout the growing season. So depending on what is the need, we can, just select what kind of strategy we want to use. So the first one, withholding the irrigation at different growth stages, is usually used when there are pumping restrictions, for example, in Western states. However, if we have insufficient pumping capacity, for example, what happened in last year, 2021, when we had in many places, mostly in central states, where we have reduced well levels, we could use this strategy where we can reduce the percentage of total water that we apply to our crop throughout the growing season. And we expect that doing that in places like Minnesota, where we have humid climate, we don't reduce the yield that much and maintain the crop yield to optimum levels. And we will see those results in the coming slides. So the two major inputs to crop production, as you know, nitrogen and irrigation. So both of these are interdependent. So if we apply less water and more nitrogen, the crop will not be able to uptake that nitrogen without water and use all of that nitrogen. So that nitrogen is going to stay in the soil or lost due to various channels. So there is a need that this nitrogen that we apply should be correspondingly adjusted to optimize the economic crop production under water limiting conditions. So if we are using some kind of deficit management or reduced irrigation, this nitrogen level that we apply needs to be changed as well as we change the water input to the crop. So knowledge about the plant response to nitrogen fertilizer and irrigation water is very essential in developing these best management practices for deficit irrigation management. For now, what Fabian and other nitrogen management specialists worked here in the state are basically concentrated on 100% irrigated or rain-fed regions about the nitrogen recommendations. But there is very less research that looks at how the nitrogen recommendations or nitrogen amounts change with change in irrigation levels. So how much water we put on also changes the nitrogen requirement of the crop. So that's what we are trying to find. So some research questions that we want answers for is that could deficit or limited irrigation is beneficial in reducing the water quality and quantity problems in Minnesota. So I highlighted quantity because quantity is something that is, at this point, is not very prevalent in the state, but as you see, the last year was a drought year. We had some issues with the water levels or the well water levels. So this could be something we have to, put our effort on. So we have to see how these strategies are, how we can best manage the availability or the water resources that we have, along with the water quality problems that we are facing right now. So we cannot just leave quantity part out. I know there's no problems of quantity, but there could be some problems in the coming years, as we expect. Then the second question is, how much reduction in yield should we expect if we use limited irrigation? Our goal is to not reduce the yield. So we are trying to find those optimum levels of irrigation and nitrogen that do not reduce the yields. But if so, how much yield reduction happens with these irrigation management techniques, and then how much adjustment in nitrogen rate should be done under these reduced irrigation rates to optimize the economic production. So these are some questions that we are trying to answer. So we conducted this research, and we are right now conducting its ongoing research that we are conducting at 2 research sites. So this map here shows you the precipitation or the normal annual precipitation in inches, and we selected these 2 sites, Becker Sandplain Research Farm and Roshold Farm in Minnesota. And this We wanted to make sure that we cover most of the central Minnesota and also different weather or climate regions in the state in this irrigated region. So that's why we selected these two sites, and we are conducting the same research at both sites. So this is the experimental design. We are looking at 4 irrigation treatments: full irrigation, 100%, 75% of full irrigation, 50% irrigation, and rain-fed irrigation. The right hand side picture on the top is the Becker Research Station. The bottom is the Rochold Farm. So same design. We have 4 irrigation treatments, 6 nitrogen rates starting from 0 to 350 pounds of nitrogen per acre. And we are putting this nitrogen urea application at split applications at V2 and V8. So 1/3 nitrogen at V2 and 2/3 at V8. So total, we have 24 treatments, which is a combination of 4 irrigation and 6 nitrogen rates. And we are replicating that 4 times. So the figure on the right on top is, you see these red boxes are the replications. Within that each red box, we have these 4 main plots, which are the irrigation plots. And within each irrigation, we have 6 nitrogen rates, that is 0 to 350 pounds of nitrogen. And as I said, this is an ongoing study. We have conducted it for 2020, 2021, and this year would be the last year. So the funding comes from the AFRAC, Agricultural Fertilizer Research and Education Council, for 3 years. But our hope is that we keep on continuing this work, because developing the BMPs require long-term data. So this will give us some idea of how these strategies work, what kind of results we should be getting, but to come up with a BMP, I think more years of research is required. So today I'll be showing you mostly the 2020 results and some yield results from 2021. But just going back to the irrigation treatments, mostly the question is being asked, what is 100% irrigation? So I put this figure. These are just some main components of soil water. So 100% irrigation is to keep the water between field capacity and irrigation trigger. So irrigation trigger is mostly 50% of plant available water, whatever water is available between field capacity and permanent wilting point. Mostly the 50% of that, when the water is depleted, 50% of that plant available water, we trigger our irrigation. And for our 100% irrigation, we fill the soil profile back to field capacity. That's our 100% irrigation. So we have soil moisture sensors that are installed in all of our plots in the study. We monitor those soil moisture. We know the water holding capacity of our soil. So we know how much water is left in that zone. So based on that continuous soil water measurement, we decide our 100% irrigation. For our 50% and 75%, we reduce that amount to 75% and 50%. So that's how we carry our irrigation treatments. In terms of measurements, we do several measurements. As I said, we have 24 treatments replicated 4 times. So we have 96 plots at each site. We are measuring soil moisture from 3 replications from 72 locations at each site. So throughout the growing season, using the neutron probe, which is one of the accurate methods of measuring volumetric water content, we go out in the field, we measure soil moisture at various depths, up to 4 feet of depth in the soil root zone, and calculate how much water is there in the soil profile. And based on that, we recommend the irrigations for our treatments. This data also helps us later when we want to look at the crops, the water balance of the whole system, to calculate the crop water need. So the crop evapotranspiration data and the drainage data, that how much is going below the root zone, to calculate the nitrogen loads. So soil moisture measurements are really, really important. The second measurement we do is the nitrate nitrogen concentration using suction cup lysimeters. So we have 196 permanent suction cup lysimeters at each site. So each of our plot has 2 suction cup lysimeters that we collect water samples from each week and then send them to lab for nitrate nitrogen analysis. So we want to know how much water is leaching below the root zone, as well as how much nitrate it is going to be lost through that water. So we have all that data as well. So this picture here shows you the suction cup lysimeter that we use. It has a porous cup at the bottom that collects the water. Then we also do plant sampling throughout the growing season at V8, R1, R6 growth stage to understand the nitrogen uptake by the crop under these different irrigation and nitrogen treatments. So just some pictures about lysimeter installation. As I said, these are permanent lysimeters. So we have put everything below the ground. Nothing is out of the ground except these pipes that you see on this number 5 picture. So we sample all of our lysimeters out of these pipes. So everything is, so there is no obstruction to farming practices that we do on the farm. So everything is underground, and these are permanent. So they are not going to be used for this research only. We have opportunity to do lots of research on these research sites in the future as well, because we have this infrastructure now. All right, so looking at the rainfall for 2021, 2020 and 2021, and you know that how contrasting these years were. So the top figure is the Becker research farm and the bottom is Westport. I intentionally put only the growing season, so May 1st to October 30th. So the left bars are 2020 growing season, the right one are 2021, and you can see a big difference. And I did some calculations from June 1st to August 15, which are very water sensitive time for the corn growth. In 2021, we got 11 inches of rainfall, whereas in 2021, we got only 3 inches at Becker. And at Westport, for the same time period, in 2020, we got 14 inches. In 2021, we got only 4 inches. So you can see how contrasting these years were, and that is also reflected in our results. So contrasting results for these 2 years that we have. So this slide shows you the relationship between nitrogen and grain yield. The left graph is the Becker research farm. The right is the Roshold. Both graphs, x-axis is nitrogen in pounds per acre, and y-axis is grain yield. This is 2020 result, and what we can see here is that the irrigation treatments, which are represented by these 4 lines here, are not significantly different from each other in terms of grain yield. There is slight decrease in grain yield under rain-fed, even in the wet year, which is 2020. However, the irrigation treatments, if you look at these 3 lines, which is blue, orange, and gray line, we don't see any significant difference in grain yield in 2020. And that's same for both sites. The EONR, which are these big dots, the economic optimum nitrogen rate, lies somewhere between 210 and 280. I don't have the exact number in this slide, but for both sites, for all of these irrigation treatments, we did not have very big difference in EONR for the first year. So all of these are in the range of 210 to 280. However, for Roshold farm, for Westport site, the EONR was slightly low and yield was also slightly lower than Becker. For the first year, the EONR is around 210 pounds of nitrogen per acre for all of these irrigated treatments. For 2021, totally different results. We had significant grain yield differences. And you can see the left graph, which shows you Becker. In rain-fed plots, we had almost no yield, so almost 0 yield in these treatments, and also big differences in irrigation treatments. Except this 0 pounds of nitrogen treatment, all of these irrigation treatment, there's a significant difference in grain yield at all levels of nitrogen between these irrigation treatments. And we have slightly different results for Roshold farm, though the grain yield at rain-fed is almost not 0 at Roshold, but very low, which does not make any economic sense here. So no yield almost in rain-fed plots. However, the difference between grain yields between irrigation treatments was not very significant. So we did not find any significant results, significant differences in grain yield in between different irrigation treatments at all nitrogen rates. And that shows us something, that the site has differences. So the weather at the site, the temperature, the rain, all plays a role in deciding how much yield we are going to get under different irrigation regimes or irrigation treatments. The EUNR, same as last year, at Becker was around 210 to 50 pounds of nitrogen for all treatments. And for Roshold, they are slightly lower than Becker, around 210 to 240 pounds of nitrogen per acre. We also, as I said, we measure soil moisture throughout the growing season. So we use water balance technique, that how much water is going in the system, how much water is going out of the system. So we calculate this evapotranspiration, which is how much water crop is using, and develop these relationships that are really important to understand the response of crop yield to crop evapotranspiration. So what we found, so the x-axis here is the seasonal evapotranspiration, water balance ET, and the y-axis is corn yield. The left graph is Becker, the right one is Roshold farm. So we found a positive linear relationship for all irrigation treatments. However, this relationship was more stronger at Becker site as compared to the Westport site. And the variation in the linear slopes at sites can be due to the differences in seasonal precipitation and distribution, how the precipitation fell, soil characteristics, and other climatic conditions. So we found that there are some differences between sites, not just the irrigation treatments, but sites also behave differently in terms of how they respond to different irrigation and nitrogen levels. We also looked at the relationship of seasonal irrigation with corn yield, and what we found in general, the higher nitrogen treatments typically have greater increase in grain yield with increasing irrigation water than lower nitrogen rates. So the left graphs are Becker for 2 years, 2020 and 2021, and the right graphs are Roshold farm 2020 and 2021. And we can see the differences in the sites as well as differences between the years. So the first year, the grain yield increase with increase in irrigation wasn't that significant. We found some increase at higher nitrogen rates. However, for the lower nitrogen rates, sometimes the relationship is opposite. However, in 2021, we found that linear relationship, that increase in grain yield at all levels of nitrogen. The 6 lines here are the 6 nitrogen rates. And as you increase the irrigation, the corn grain yield is going to increase, and that relationship is more stronger for higher nitrogen rates at both sites. And we also see that this is a curvilinear quadratic relationship. So we also see that diminishing curve. So as you increase the water more than what is required, there is a drop in yield as well at higher nitrogen rates. So that's not just because of irrigation, but also how much nitrogen you are putting in. So that also plays a role in deciding how much water you put, how much nitrogen you put, and if you get that diminishing curve. So higher nitrogen rates usually get that diminishing curve. Like if you apply more water, that nitrogen, that extra nitrogen that is in there in the soil profile is going to lose to the leaching. So there is a drop in the grain yield for that. And I have the results for nitrate leaching as well for 2020. So these 4 graphs are for irrigation treatments, 100%, 75%, 50%, and rain-fed plots. And these 6 lines are 6 nitrogen rates. So in general, what we found, the higher leaching, this is load, this is cumulative nitrate loading in pounds per acre from each of these treatments. And what we found is that for higher nitrogen rates, we have higher nitrate leaching below the root zone. On average, so as I said, the UNR for all of these irrigation treatments lies between 210 and 280 pounds of nitrogen per acre. So average, so if we just concentrate on these 2 levels, I did some average, and for 100% irrigation at Becker site, we have 15 pounds per acre nitrogen loss. At 75%, we have 27. We have 12 pounds at 50% and 15 pounds at rain-fed. So the highest was under 75%, whereas lowest was under 50% irrigation treatment. For Westport side, the results were slightly different. The maximum leaching was observed in 100% irrigation if we average 210 and 280 pounds of nitrogen application treatments, whereas the lowest again were in 50% irrigation. So this was 2020. Remember that 2020 was the high precipitation year. So we had almost full moisture, close to field capacity in all of our treatments throughout the growing season. There were only very few times when we had to irrigate. And that also, when we irrigate, there was rain maybe in 2 days. So when we irrigate 100%, that means we are filling our soil profile back to field capacity. And if it rains the next day or 2 days after, your soil profile is already filled with water. There is no more room for water to go in. So all that water is going to be lost in leaching. And that's what we are seeing here in 100% treatment. Whereas in 50% and 75%, we had some room for irrigation to store, so that there was less losses in nitrate leaching at Westport particularly. I'll be curious to look at 2021 results, because I'm expecting totally opposite results, because crop water use was really high, crop yields were really high in 100% irrigation. So we could expect some differences in leaching in a dry year here in the state. But for what we found, that for the wetter years, for normal precipitation, average precipitation, or above average precipitation years, there are possibilities that irrigation amounts can be reduced throughout the growing season. So our 50% and 75% results are very promising in terms of yield, maintaining the yield, and also in reducing the nitrate leaching losses to the groundwater. This is very basic economic analysis. I thought it would be interesting to show you some economics, but all of this boils down to the cost of irrigation. Here at this point in the state, water is free. There is no cost to water except the energy cost that you spent for irrigating that water. So this could be different. So I used irrigation cost at $16 per acre inch, which is the US average, so all states average. However, in Minnesota, our energy cost, if we don't add any value to water, our energy cost on average is $5 per acre inch. So I did some economic analysis. I know lots of data on this table, but just concentrate on the highlighted values, and I can walk you through it. So the left table is the Becker research farm in 2020, and what we found in terms of net income. So net income is when we subtract the nitrogen cost and irrigation cost from our gross income that we make from yield. We found that on average, the highest net income was under 50% irrigation. And similar results for Westport side. We found 50% irrigation to be most economical in terms of the monetary benefits, as well as I showed you the nitrate leaching graphs. At both locations, our minimum nitrate leaching for the average of 210 and 280 pounds of nitrogen per acre was under 50% irrigation. However, for 2021, I'm not able to move the slides. Okay. For 2021, the similar tables, so the Becker is on the left, Westport is on the right. We found that 100% irrigation, because there were significant differences in grain yield, the 100% irrigation made the most sense. The reason behind, as you know, 2021 was a drought year, very dry season, no rainfall in June, July, and August. So crop needed that water. So as much as we were putting in, crop was actively using it. So all that water was being used by the crop, that reflected in yield as well. But as for our 75% and 50%, the water deficits were really high, water was stressed. So there were crop yield losses. So reduced irrigation, from this study, what we see, reduced irrigation does not make sense for years that we experienced in 2021, which were really dry. So we really need irrigation in those years. So in summary, for this project, we found that higher evapotranspiration values were observed at Becker Research Farm than at Westport due to higher evaporative conditions and earlier leaf area development in response to warmer conditions at Becker than at Westport. So the weather plays a really important role. The location of your field, where the field is and how the climate behaves, the water use really depends on those factors. We also found a positive linear relationship between corn yield and evapotranspiration for all of our irrigation treatments, which this relationship was more stronger at Becker site as compared to Westport site, and that also comes down to how the climate was at each of these locations and how the soil types were at each of these locations. There are variations in the linear slopes, as I said, and then, as I said, most of that is reflected in seasonal precipitation and how the precipitation was distributed throughout the growing season at both of these locations. We did not find any significant differences in grain yield between irrigation treatments in 2020. However, these differences were really, really significant in 2021, 100% being the highest grain yield and rain-fed almost no yield. Maximum nitrate leaching was observed in 75% at Becker and 100% at Westport, which are higher irrigation treatments, and 50% had the lowest nitrate leaching at both sites in 2020. And then, as I said, this is an ongoing research. We will be conducting this year and maybe have some conclusions at the end of the 3 years of this study. All right, changing some gears. So variable rate irrigation or precision irrigation management is not a new, people say it's a new technology. It's not new, it's here from last, how many, 40 years, 30 years, it's in existence, but the adoption of these technologies are very low because mostly we don't know how to use them. They're expensive. There's very less research on how they behave in different cropping systems, in different locations, in different climates, in different soils. So that's what we are trying to find here. So most of these studies, they require bigger fields. So 120, like quarter section for irrigation studies. This kind of research cannot be conducted on small plot studies. On small plot studies, we can, find some scientific answers about how the water behaves under different nitrogen treatments, how it behaves under different soils. But in order to get some data about how these technologies work under production systems, under bigger farms, we have to conduct these under full center pivot systems. So that's why we started this study in collaboration with our grower partner from Stearns County in Belgrade. So we are conducting this variable rate irrigation study on his farm in order to understand how, when we apply water based on the soil's properties, how it impacts yields and how it will help us in reducing the nitrate leaching losses, as well as helping us in saving some water when we don't need it, where we apply it. So basically, the goal is to evaluate the impact of this variable rate irrigation technology in comparison to conventional uniform rate. So uniform rate is when you apply same amount of water, no matter if there is any soil variability that exists in your field. So you apply same amount of water throughout the field. Whereas the precision irrigation or variable rate irrigation is applying only that amount of water that is required by the soil, by the crop, within that field. So this is an example where we conducted this study this year. So the first map shows you the soil map. So this field is highly variable. There are like 5 types of soils that exist in this field. We then looked at the elevation map. The center map is the elevation map, and the rightmost map is the electrical conductivity map. So you can see all of these 3 things are, if you look carefully, they are following the same pattern. So the higher elevation, the higher EC, which is the red color, is also the lower elevation and the different soil type, whereas this brown soil type, which is lower available water capacity, has higher elevation and lower electrical conductivity. So through literature as well, and this is one example, but through literature, we also found that electrical conductivity of the soil is very related to how much water the soil can hold, so available water capacity. So that is something that can be used for creating the management zones for irrigation, and that's what we did. So this electrical conductivity mapping was done by Josh Stemper, who was an irrigation specialist at UFM in 2015 for this same field where we are conducting this research this year and last year. So the EC mapping was already done. So we created these EC maps and created the management zones based on the different EC electrical conductivity of the soils. So for this particular map, we created 3 zones. The blue zone is the low electrical conductivity map, which also has the same the soil type, which has the lowest available water holding capacity. The yellow is the middle from 7.3 to 11.5 electrical conductivity. So that's our middle zone, which is like medium water holding capacity. And the red zone is our depressional, which has very high water holding capacity, very low elevation. So these soils are prone to water stagnation. So when rain happens, water stays there for a very long time. So those are the depressional soils in the field. So we did this management zones, and then we divided our field, which is a quarter section field, into 6 pie-shaped plots. So you can see on the screen here, the VRI are these 3, the 2 pies on the bottom and 1 on the top left is the variable rate irrigation treatment. The URI is the uniform. So in uniform rate irrigation treatment, we applied same amount of water, no matter how many zones exist in this pie. Whereas in VRI plot, we irrigated based on the management zones. So if 3 management zones exist in this VRI, we irrigated based on those zones for the VRI plot. So this is our prescription map. The irrigation system that was on the field was a valley irrigation system. So we use the valley software for doing that. So you can see this green color is the 100% irrigation. So our uniform irrigation plots got same amount of irrigation no matter how many zones exist. However, our VRI plots, which are these 2 bottom and 1, we irrigated based on the zones that we developed. So just to show you that this small box is the irrigation zone, so that can be irrigated differently. That's how the variable rate irrigation. So it changes the water, how much water is being applied or going through those nozzles. So each bank of nozzles can be 1 zone. So this smallest box is what is 1 zone in that field. And these are the available water holding capacity at 50% management allowable depletions for all of 3 zones that we had, zone 1, zone 2, and zone 3. So no matter if we are irrigating in uniform rate irrigation or variable rate irrigation, we have to know that how much water is required, even for 100% irrigation, right? So we apply, we install these soil moisture sensors, and you can see the location. So these dots shows you the locations where we put the soil moisture sensors up to 2 feet of soil profile, as well as lysimeters to understand if there are differences in nitrate leaching between VRI and URI. So we put this Acclima TDR sensors that gave us data online on our mobile phones or desktop, so that we can monitor this hourly soil moisture data and schedule irrigation based on the soil water. At the end of the season, the grower gave us the grain yield data from his combine, and then we cleaned that data. We wanted to compare these pies. So the shape of the field wasn't very good. So it's very uneven. So we had to cut down for our yield analysis. We only use the data for inside 5 spans of the irrigator so that we can compare the equal size pies for our yield measurements. These are the final results for this year. This is a 2-year study. This was the first year, which happened to be very dry. So we found very good results, but I'm expecting some, and I'll share that with you. So irrigation on uniform rate irrigation, or zone 1 of which is the highest irrigation requirement zone of the field, was 11.6 inches, around 12 inches of irrigation, whereas zone 2 and zone 3, which were reduced irrigations, had 5.8 and 2.3. So overall, on average, we applied 11.6 in uniform rate irrigation, whereas 6.6 inches of irrigation in VRI. The grain yield on average was 258 and 242 for these treatments, but which is not significantly different in terms of how much water it saved. So if you look at irrigation water productivity, which is how much yield bushels per acre inch was bushels produced by per acre inch, you can see we have like high irrigation water productivity for VRI. So as I said in my previous research project, that it all comes down to the value of water, that how much value water has. So in this analysis also, I use $16 per acre inch, and we can see the net income after subtracting the irrigation cost from the gross income. We do not have any significant difference between URI and VRI, whereas we are using half of the water that we are putting on, so 12 inches and around 7 inches in VRI. So and last year was very, very dry year. Even the depressional areas where we applied 2.3 inches of water needed water for crop production. I'm not expecting this to be happening in the years that we usually have here, which is average precipitation or above normal precipitation years. In those times, I think we can reduce our irrigation requirements way more than we reduced in this first year, which was a very high irrigation requirement year. So I'm expecting some better results than this for the next year if the weather stays as we are expecting it to stay. Just 2 slides left. So as I said, whatever irrigation management strategy you use, deficit irrigation, variable rate irrigation, it all comes down to irrigation scheduling. So if you are not using any scientific irrigation scheduling method, no matter, so the 100% irrigation, throughout my presentation, I talked about 100% irrigation. So that's your base for deciding anything, for deciding any VRI, any deficit irrigation. If you get that 100% wrong, I think everything is, all that calculations are wrong. So to get that irrigation amount that you need to use some kind of irrigation scheduling method. And there are various kinds of irrigation scheduling methods that you can use. You can use soil moisture sensors. You can use weather data, your ET from your weather station to calculate your irrigation requirement. And there are other commercial systems, integrated systems that you can that can come on your mobile phone, and you can just look at them. But they are of course associated, have some associated cost. So here we are trying to figure out what we can as university can give to the growers is. So we are working on this irrigation management assistant tool, which is in existence from 2015. So original funding came from LCCMR in 2015, and Benton County and RESPEC, which is a private company, developed this irrigation management assistant tool for Otter Tail County area and Benton County area. So this tool is an online tool that uses weather data, crop water balance, and gives you irrigation requirement. What we are trying to do is, we got this funding last year from LCCMR again to update this tool, to make it more accurate, and to expand it throughout the state, free of cost for all the growers to be used. So that's our plan, to give this tool out for all the counties in Minnesota by the end of 2023. For this year, however, we are only expanding it to 11 counties, including where it already exists, but also adding some additional counties like Stern County and Pope County and Sherburne County, and try to work with growers who we are calling IMA champions, to work with them one-on-one and ask for their feedback in order to update this tool. So if you are interested, if you are having contacts or interested in to be part of this program, just reach out to me. We can work it through. So we are trying to figure out how we can make changes in the model that already exists in the tool in order to make it more accurate. So to make some changes in the rainfall prediction, make some changes in the evapotranspiration model, and then how we can use some machine learning tools to make it to remove that error that propagates. So also using some sensor technology to use the machine learning. And then we right now the tool is being branded as RESPEC. Our hope is that with this new money, by 2023, we are going to be branding it as a University of Minnesota Extension irrigation management assistant tool. So stay tuned. And if you have any questions regarding that, if you want to be involved, reach out to me. I would like to acknowledge all the funding agencies. So for our irrigation nitrogen project, the funding comes from AFRAC and MDA. For our VRI project, Agri Sustainable Demonstration Grant Program. And I would also like to thank our farmer collaborator, Grant Anderson. For the IMA tool expansion, we are getting the money from LCCMR. And I would also like to thank our field crew and grad students who are working on all of these projects. Thank you. First question is, it seems like intensive agronomic management showed more positive results. Any idea as to why? Is it? I think this was for the previous.
Yeah, probably.
Right, yeah. Okay, the next question is, could the difference at Rochelle be the timing of rain? Yes, I think so. So the timing of rain was very different at Westport for both years, for 2020 especially. We were actually kind of finding for time to irrigate because we wanted to irrigate. So in 2020, it was I think all boils down to timing of irrigation. We had like very good rainfalls in the very critical part of the growth stage as well in June, July. And when we irrigated, the rain happened right after the irrigation, maybe in 2 days. That we can also see in the nitrate leaching results that we had more nitrate leaching in 100% irrigation because of that rainfall timing. The next question is, why did 75% at Becker lead to highest N leaching compared to 100% at Westport? So the values that I showed you were the average of all the irrigation, the nitrogen treatments. However, if you see, most of that high nitrate leaching happened in very high nitrogen rate plot, like 350, 280, and 210 pounds of nitrogen per acre. I think the reason behind that is that when we apply more nitrogen and reduce levels of irrigation, like 75%, there was less water for the crop to take up that nitrogen, and then most of it was in the soil profile that was being leached. I think that was the main reason, and also comes down to the crop vigor. So when you have differences in how the stand, how the crop is, it also changes how it is using that nitrogen and water from the soil profile. So what we think is that under 75% irrigation, the crop wasn't, because of reduced levels of irrigation, wasn't that, the leaf area index wasn't that high that it could take up all that nitrogen in high nitrogen rates with that amount of water that we applied. So that could be the reason.
Right. To keep moving on.
Thank you. Yeah.